Hi everyone, this is Edward Lamb from Monash University. This talk is about large neighborhood search for temperature control with demand response. In this paper, we study a real problem in the energy domain. We have several buildings connected to a microgrid. A microgrid is a small electrical grid that is close together. On very hot days, there is not enough power to run the air conditioning systems of all buildings at the same time. So we want the microgrid to centrally control when the buildings should turn off their air conditioning. For example, some buildings may have better insulation than other buildings, so these buildings can run their air conditioning for less time overall. We want to control the air conditioning systems in all buildings so that the occupants are comfortable. We apply machine learning and optimization to the problem. We collect temperature data from each building and we train the neural network on the temperature data. This model predicts the next temperature given the current temperature and some environment inputs. And then we embed the trained neural network into a quadratic programming model. This optimization model copies the neural network for each building and each time step, and then we optimize over all buildings and time steps to decide which buildings should turn on their air conditioning during which time step. We also developed 6 neighborhoods in a large neighborhood search. Each of these neighborhoods aim to improve the solution in a different way. We solve the optimization model using constraint programming and mathematical programming with and without the large neighborhood search, so we have 4 methods in total. For constraint programming, we use G-code, and for mathematical programming, we used Gurobi. Our experiments show that LNS in constraint programming finds the best solutions. Hi everyone, this is Edward Lamb from Monash University. This talk is about exact approaches to the multi-agent collective construction problem. Let's consider a planning problem in robotics. On the right side, there's a picture that shows a 3D structure. This structure is made up of several grey blocks. In this problem, we have a set of robots, and the task is to get the robots to build this structure in a swarm-like manner. So the robots begin off the blocks world, and then they enter the blocks world carrying blocks, and they need to rearrange the blocks to build this structure. Sometimes they will need to construct ramps to use as stairs to access the higher levels of the structure, and then after they are done, the robots need to deconstruct the ramps and remove the ramps off the blocks world, leaving the structure intact at the end of the planning horizon. Presently, all of the existing approaches are based on heuristics, and the state-of-the-art is based on a multi-agent reinforcement learning approach. So we try to study this problem using exact methods. We constructed an integer programming model and a constraint programming model to solve this problem. Our integer programming model is based on a network flow, and our CP model is also based on a different type of network flow, although we did try sequencing CP models in the past. Our IP model takes up to 7 days to solve optimally some of these very simple instances that appeared in the state-of-the-art reinforcement learning paper. We tried it on 6 instances, and the IP model took up to 7 days to solve. The CP model wasn't able to solve these instances optimally, even though they were actually very tiny. So in our conclusions, we found that the IP model was better than the CP model because the IP technology was able to exploit these network flow structures much more effectively. And the CP model probably didn't perform as well because it had a lot of weak propagation coming from disjunction and implication constraints.
Hi, I'm Begum Genç. I'm a postdoctoral researcher working at University College Cork. In this video, I will present you our application paper with Barry O'Sullivan that's on solving the examination timetabling problem at University College Cork by using a two-phase constraint programming model. In the video, I will first talk about the problem definition and some constraints of the problem, and then I will present you our proposed two-phase constraint programming model in detail, then provide a discussion of the decomposed models, and I will conclude my presentation by showing some empirical results. The examination timetabling problem in general is about finding a suitable time slot and a venue for each examination by respecting the hard and soft constraints given by the institution. So in this work, because it's a real-world problem from UCC, it's not very easy or it's not really possible to relax the hard constraints. So the problem becomes a bit difficult when you are dealing with the real-world problem. And when we look at the problem size, we have a fairly large model, and our aim is to build an inclusive and fair model for the students. So we want to increase the fairness measures, and we are including all the students that have some special needs in our model. So the special needs students may be students with some requests, such as they must sit an exam on their own in a separate venue or in a shared venue or in a lab, but they must be seated away from the main groups. And this is how our model looks like in general. In phase 1, we are assigning each exam into we are assigning each exam a time slot, and then in phase 2, we are assigning each exam into a room during the given time slot. And both of our phases are heavily relying on the bin packing constraints. Especially in the second phase, we are dealing with the bin packing with fragmentable items problem, which is interesting because we noticed that the constraint programming community have paid little attention to this problem so far. And this is how our results look like. We are significantly improving the UCC's current schedule. And we think that this work is especially important at the moment because due to the pandemic-related constraints, such as the social distancing measures, it's not practical for institutes to hold exams without allowing split exams anymore. So the institutes can tailor this model to their needs, and they can figure out what is the minimum number of rooms required for them in order to hold physical exams in the institutes. So thank you for listening to me. In the rest of this presentation, I will talk about the details of our work.
Hello everyone, my name is Monika Trimoska and I will be presenting the paper XOR Reasoning for the Index Calculus Attack. This is joint work with my supervisors Sorina Ionica and Gilles Dequin, and we are all from the University of Picardy in France. In our paper, we studied the use of SAT solvers in cryptanalysis. This field is commonly known as logical cryptanalysis, and thus we will start the presentation by explaining a bit how this method works. After that, we will mostly focus on the XOR operator, as this operator is extensively used in cryptography. I believe this is the reason why there has been significant research efforts in combining XOR reasoning into SAT solvers in the past years. And these XOR-enabled SAT solvers use a special form which is a mix of OR constraints and XOR constraints. It is always a better idea to use this form instead of transforming the XOR constraints into their equivalent CNF. Because with this form we can use algebraic solving techniques such as Gaussian elimination, and these techniques have been shown very powerful in solving these types of systems. However, in our work we have detected a use case where a Gaussian elimination in SAT solvers is not as efficient as Gaussian elimination in algebraic techniques, and then we have found a way to solve this. So we will continue by presenting our SAT solver, which is built from scratch and is DPLL based. Our solver is comprised of 3 modules: the CNF module that does the unit propagation as you know it, and 2 XOR reasoning modules. After presenting our solver, we will present our pre-processing technique, which is inspired from graph theory. More specifically, we will show you how we use the minimal vertex cover problem to decide on the order of branching variables. At the end, we will show you our experimental work, which is mostly focused on the elliptic curve discrete logarithm problem. This problem is at the core of many public key cryptographic systems. There are many ways to attack this problem, one of which is the index calculus. And the index calculus attack goes in 3 phases. One of these phases can be reduced to solving a Boolean polynomial system. This system is usually solved using algebraic techniques such as Grosvenor basis, but in our work we have tried to replace Grosvenor basis with our SAT solver. Our experimental work shows that our solver is more efficient than Grosvenor basis for this problem, which was the main goal of our work, but it is also more efficient than state-of-the-art SAT solvers for this particular problem.